Welcome to our university lecture on mosquito control strategies. Today, we are going to explore the scientific and mathematical methods used by public health officials to combat mosquito-borne diseases. Whether you are completely new to this topic or looking to deepen your understanding, by the end of this session, you will understand exactly how to effectively manage and reduce mosquito populations to protect communities. Let us begin with our first major strategy, known as source reduction. Imagine trying to stop a leaky roof by constantly mopping the floor instead of fixing the hole. That is exactly what it is like if we only try to kill adult flying mosquitoes without stopping them from being born. Source reduction is the ultimate strategy of fixing the hole. By draining swamps, emptying artificial containers like old tires, and managing irrigation systems, we physically remove the aquatic environment necessary for their development. This proactive approach permanently reduces the carrying capacity of the environment, stopping the problem before it even begins. Now that we understand what source reduction is, we must ask why it is so critically important. This strategy is the most sustainable and environmentally friendly approach to mosquito control available to us. If we do not eliminate these breeding sites, we will be forced to rely heavily on toxic chemicals, which can harm other wildlife and eventually lead to severe insecticide resistance. Source reduction provides long-term protection and truly forms the backbone of any integrated vector management program. Without it, all other control methods are merely temporary fixes that will eventually fail. To know if our source reduction is working, we need a mathematical way to measure it. This brings us to the Brito index. This formula helps public health officials quantify the risk level in a specific community. BI represents the Brito index itself. C is the total number of water-holding containers found with active mosquito larvae living in them. H is the total number of houses inspected in that area. We multiply by the constant 100 to express the index per 100 houses. If the number of positive containers increases, the index goes up, indicating a much higher risk of disease transmission. Before we move on, let us see this with a concrete example. A public health team inspects 250 houses and finds 45 artificial containers with mosquito larvae. We need to calculate the Brito index. First, we identify our variables. C is 45 and H is 250. We substitute these into our formula, dividing 45 by 250, which gives us 0.18. Multiplying by 100 gives a final Brito index of 18. This means there are 18 positive containers for every 100 houses, indicating a high risk that requires immediate cleanup. While source reduction is our long-term solution, sometimes we face immediate, life-threatening emergencies. Think of chemical control as the emergency brake in a car. When a disease outbreak, like malaria or Zika, is actively happening, we simply cannot wait weeks for source reduction to work. We need an immediate way to knock down the adult mosquito population that is currently flying around and biting people. Chemical control involves applying synthetic or naturally derived compounds like larvicides in water or adulticides sprayed onto surfaces to rapidly paralyze and kill these dangerous insects. Because chemical control is so powerful, it comes with significant responsibilities and must be used carefully. Overusing these chemicals leads to insecticide resistance, where mosquitoes actually evolve over generations to survive the poison. Furthermore, these chemicals pose potential risks to human health and can severely harm non-target beneficial insects like bees. This is exactly why precise application is mandatory for public health workers. Applying too little leaves the population intact and encourages resistance, while applying too much is highly toxic, expensive, and wasteful. To ensure we apply exactly the right amount of chemical, we use the dosage formula. V represents the total volume or mass of the commercial insecticide needed. D is the target dosage of the active ingredient required per unit area. A is the total surface area we need to treat. Finally, C is the concentration of the active ingredient in the commercial formulation, which we must express as a decimal. If the target area increases, the required volume increases. If we use a more concentrated chemical, the required volume will decrease. Let us apply this formula to a real-world scenario. A health worker needs to spray the interior walls of a house. The total area is 150 square meters. The required dosage is 0.2 grams per square meter, and the powder concentration is 50%. We first convert the 50% concentration to a decimal, 0.50. Multiplying the dosage by the area gives us 30 grams of pure active ingredient needed. Dividing this by the concentration factor gives a final answer of 60 grams. The worker must mix exactly 60 grams of powder to achieve the lethal dose safely. This diagram visually summarizes the chemical control process we just calculated. You are looking at a cross-section of a house where a health worker is performing indoor residual spraying. Notice the worker in protective gear applying the spray to the inner wall, which represents our target area, A. The stars on the wall indicate the treated surface. As the mosquito vectors come into contact with the treated wall, they experience a knockdown effect and fall to the floor. The formula box reminds us how the precise volume was determined to make this intervention both safe and effective. Moving away from synthetic chemicals, let us explore a more natural approach. Imagine hiring a natural security guard to patrol a pond and eat any intruders. That is the essence of biological control. Instead of using artificial chemicals, we introduce natural enemies of the mosquito, like larvivorous fish or specific bacteria, into their habitat. These agents specifically target the aquatic immature stages of the mosquito. It is an incredibly elegant method because it is highly specific, environmentally safe, and often self-sustaining once established. To evaluate how well our biological control agent is working, scientists calculate the population reduction percentage. In this formula, R represents the percentage reduction. P sub I is the initial population density of mosquito larvae before the biological control was introduced. P sub F is the final population density after the treatment. We subtract the final population from the initial to find the absolute decrease, divide by the initial population, and multiply by 100. If the final population drops to 0, the reduction becomes 100%, proving the intervention was highly effective. Let us see how this calculation works in the field. A municipality has a pond with an initial population density of 400 mosquito larvae per square meter. After introducing mosquito fish for a month, the final density drops to 24 larvae per square meter. We plug these values into our formula. Subtracting 24 from 400 gives us 376, which is the actual number of larvae eliminated per square meter. Dividing 376 by the initial 400 yields 0.94. Multiplying by 100 gives a final answer of 94%. This proves the mosquito fish were highly successful. We have covered a lot of ground today. So let us review the most important ideas. First, source reduction is the ultimate sustainable strategy because it permanently eliminates mosquito breeding habitats. Second, when immediate action is needed during an outbreak, chemical control provides a rapid knockdown, provided we calculate the dosage precisely. Third, biological control offers an eco-friendly alternative by using nature's own predators to keep mosquito populations in check. By combining these strategies and measuring their success mathematically, we can effectively protect human health from vector-borne diseases. Great job following along with these concepts.